Hello students, welcome to the presentation on helical gear design. In this presentation we will see the procedure of designing the helical gears. Here just is a comparison of the helical gear tooth with the spur gear tooth. You can see the tooth here are parallel to this axis of the gear blank, but here the tooth are at certain angle to this axis of the gear blank. So the inclination of this gear tooth with this axis is the helix angle. Now in this helical gear geometry, these are the helical tooth cut on the gear blank, and this is the plane BB which is normal to this gear tooth, but whereas another plane AA which is normal to the axis of the gear shaft. Now in this you can see this angle beta is the helix angle, and this is the plane of action. In this plane the forces will act. This is the transverse pitch, normal pitch, and see in this plane which is at the inclination of beta called as helix angle, we define the normal module, and in this plane we define the transverse module. Now here BB, this plane is the normal plane, AA is the transverse plane, FT is the tangential load coming on the gear tooth, FA is the axial or the thrust load, and then beta is the helix angle, PT this is the transfer pitch, PM is the normal pitch, B is the phase width, okay, and Mn is the normal module which is given by Pn divided by pi. Now here in the helical gear system we define formative or equivalent number of teeth. It is defined as the number of teeth that can be generated on the surface of a cylinder having a radius equal to the radius of curvature at a point at the tip of the minor axis of an ellipse obtained by taking a section of gear in the normal plane. So this is the section taken in the normal plane, and this is the center, and this is the tip of the minor axis. So whatever the teeth are there on this is the formative or equivalent number of teeth, and for determining the form factor, Lewis form factor, the equivalent number of teeth will be utilized. Now coming to the steps involved in the design of the helical gear, in the first step, as usual, we will determine the velocity ratio given the speed of the pinion and the gear, or number of teeth on the pinion or gear, or diameter of the pinion or gear, or even the speed ratio itself is given, and one of the parameter either N1 or N2 or D2 or D1 or Z1 or Z2, other parameter can be determined. Now second thing is to find out the design stress for gear and pinion, that is sigma D1 and sigma D2 respectively, from the table 12.7 page 34, that is K. Balavar Reddy and Mahadevan data handbook. Then find out the virtual number of teeth on pinion and gear, and for determining the virtual number of teeth on the pinion and the gear, these equations are being used. ZE1, equivalent number of teeth on pinion, equal to actual number of teeth on pinion divided by cos cube beta. Beta is the helix angle, and these are available on page 211 as equation 12.22a. Then find out the Lewis form factor based on given helix angle. If helix angle is not given, assume it to be 20 degrees, that is beta equal to 20 degrees. In the Lewis form factor equation, virtual number of teeth ZE1 or ZE2 to be used instead of actual number of teeth, that is Z1 or Z2. So this care has to be taken. Lewis form factor can be calculated by using the equations 12.5, C, D and E available on page 204 of Design Data Handbook. Then after finding the Lewis form factor, we need to find out the product sigma D1 Y1 for pinion, similarly sigma D2 Y2 for gear. Then compare these two values, and whichever is smaller, that will be the weaker member, and design will be based on that member. Then step 3 involves determination of the tangential load based on the power transmitted. It is standard equation 1000 into P power transmitted in kilowatt into service factor divided by pitch line velocity. So this is equation 12.7a available on page 205. V is pi dn by 60 into 1000 in terms of meters per second. Again, the tangential tooth load is determined based on the Lewis equation, which is available on page 214, equation 12.24a, given as Ft equal to sigma d to Cv into pi into capital M into Mn normal module divided by Cw. Normally in the design of helical gears, the phase width is taken as 20 times the normal module, and this capital Y is pi into small y, that is Lewis form factor, and Cw in this equation is wear and lubrication factor available in table 2.1 on page 241, and you can assume Cw as 1.25 for all practical purposes. Now this is the table where Cw is available. For 3 different conditions, the Cw values are given. Now the Cv value, velocity factor based on velocity, can be calculated, or initially it can be assumed as 0.5. Then equating equation 1, that is the tangential load calculated based on power transmitted, and this is the tangential load calculated from Lewis equation. And when these were equated, simplify and put that in the form Mn cube into Cv. So it will be something on the right hand side. Now you have to choose the value of Mn by assuming Cv as 0.5 such that this side is greater than this side. Then after having determined the module, you can calculate the gear parameters such as pitch diameter of the pinion, pitch diameter of the gear by using the standard equations, center distance, phase width and so on. Then the tangential load Ft based on revised value of Cv. Then calculate other proportions of the gear such as addendum, addendum circle diameter, addendum circle diameter, etc. And one more parameter that comes in the design of helical gears is the axial thrust, which is given by Ft, tangential load into tan beta. Then we need to check the gears for the dynamic and the wear loads. First, we'll see the dynamic tooth load. Standard equation available in the data book for dynamic load is this one, tangential load plus incremental load, which is given by this equation, and all these terms are having their usual meaning. Okay. Only thing is here cos square beta is coming, here it's cos beta, again here cos square beta. And the calculation of this C value is again based on the velocity. You have to get the error from the figure, and then you have to move to the table, search for the nearest error that we have taken from the figure, and the corresponding C value for the combination of the gear and pinion material. Then calculate the gear load using this equation, T1 into B into Q into K divided by cos square beta, and for safe design the condition to be satisfied is the wear load should be greater than dynamic load. So this load contains the value K. So by comparing this, find out the value of K, and by referring the tables, find out the Fresnel hardness number of the pinion and gear. So that is the end of the process of designing the helical gears. We will meet in the second part with a numerical problem. Thank you.